So after some technical difficulties, we're running. So we're recording this, so I will tell a little bit the pragmatic aspects of the course first. So we have Thursday session, more practical, Friday session, more theoretical. On Thursday, we will have some lectures talking about the technicalities of and APIs of the Android development and iOS sometimes as well. Some topics are kind of generic. Some topics are specific for Android. We have the Git Lab wiki, which will be used as a main point for the course. We tried to use Blackboard last semester, and it was not working too well. I mean, you can't really refer to the discussion threads. It's really difficult to refer to content on Blackboard. And Blackboard, I mean, it's okay for announcements, but it's not very good for running the course. So we've migrated, and we are going to use Git Lab. Git Lab is sort of like GitHub, but run locally. All the data is local to the school, and your stuff is not kind of exposed. There was a comment why we don't have HTTPS. We will. We're working on it. So in the future, the connection to the local server will be HTTPS. But most of you will be accessing the server from the LAN, from the local network. So that doesn't matter. I mean, there is no sniffing going on the network. Yeah, maybe there is. I don't know. They shouldn't.
But how intimate is the information anyway?
And also, the information is not very intimate, right? I mean, most of what is there is public anyway, so it shouldn't matter. Those of you who don't have an account on GitLab, I strongly encourage you to do so, otherwise you really handicap yourself. Yeah. To a point where you will probably not pass the course because all the materials around the labs are there, right? So, I mean, there is no other way. What else we're gonna use? We're gonna use the wiki for announcing stuff. You can edit the wiki, by the way, as well, because you're part of the group. But if you do that, do it like considerate to the other users, right? So if you have some tutorial or something you can put under the tutorial, that's fine. Just go ahead and edit. But don't mess up, like don't be distractive. All of that is tracked, I think, so we can revert back to, I'm not sure about the wiki.
Wiki.
I think it is also.
It's a Git repo.
Yeah, it's a Git repo, so it should be fine.
Yeah, it is. Yeah.
Okay, so GitLab, wiki, and issue tracker. We did use it last semester for the cloud course, and it kind of works quite well. It works quite well for a number of reasons. One is that some of you will have a question which other people can benefit from. So it kind of spreads the information better than just going to Chris or me and asking, and then we answer you, and then nobody else sees that. So having it in a public sphere helps others to benefit from the questions and answers that are kind of given there. So that's one thing. The second thing is it's easy for us to have a history of what has been asked before and refer to you to that point, right? So if something has been discussed and dealt with in the past, we just say, yeah, look at the issue number 13, and then you just read and follow the instructions or whatever is there, right? So it's a repository of some hints and help for the course.
Use labels and issues?
That's right. So we will, currently, I don't think we organize the labels yet, but we will organize the issues into like Q&A, assignment 1, assignment 2, and so on. So if the labels are there, try to use them logically. Yep?
You have to give access to use the labels also.
I think because of the new setup, you should be able to do that automatically. But if you don't, make an issue, and we'll fix that. So we reorganized the access control a little bit, and I think normal logged-in users will have access now. Before, you have to be given permissions to that particular course. Now it's universal across all the courses. Yeah. Anything else about the logistics? I will make announcements through GitLab wiki as well, but I will push through your email through Blackboard. Yeah. That's pretty much it. The assignments code, because for the assignments we'll have like a skeleton code, it will be done through the Git of the GitLab, right? Currently the repo is empty. Don't mess up with the repo. I will set the repo up when we have the first assignment, and then you fork it, you do what you need to do, and then you submit your Yeah, actually, you will have to. Yeah, we will organize
Change,
it.
yeah,
Yeah,
change
we'll
the
see
screen.
how it's done. The bottom line is that we do use Git extensively in that course as well. So if you're still struggling with Git, it's the time to get yourself familiar with the tool, because all the assignments will be done through Git and all the submissions will be done through Git, as we do in number of courses. Yeah. So that's pretty much it. So this class is a little bit of an intro to the course. I will do a little bit more high-level intro tomorrow. This intro is kind of specific to Android. The class tomorrow will be more generic. We'll go look back into the history of the mobile as a as an invention, so to speak. So we'll see how the wired telephony works and how it evolved to be a mobile telephony and how the evolution of smartphones happened. We look a little bit into that today from the Android point of view, but tomorrow's lecture is more generic and more sort of core to what mobile technology is about. Right, so
Just press the button. Can you guys press the buttons on your corresponding screens so they actually switch on if you want to see anything? On the back, on the right back.
I think you can use a controller too.
no, you cannot turn physically the screens from here. If the screen is off, you have to press the button to turn it on.
Thank you.
Yeah, thanks. So the red LED should not be red at front. That means it's on. And you can watch the slides on your laptops too. It's the slide deck from the Google Slides. So if you open the slides on your laptops, you can follow as well. So I will spend this talking block to talk about Android philosophy, a little bit about the architecture, and a little bit about the history. And then we will move in to the lab. The lab is like a very rudimentary hello world, but if you can do hello world, you already know 25% of what you need to know to program on Android. So the learning curve is like super steep. Like it's not one-liner that you say hello world and it prints hello world. To do a hello world on mobile, you have to touch on a number of technologies and things that kind of make things quite complicated. So how many of you don't know Java? Crap. So why you don't know Java? You didn't have the course with Ovint about the web course, right? Okay, so
Change the prereqs.
yeah. So we will probably spend some time. I will see if I can squeeze it tomorrow in the second half, or the first part next week to talk a little bit about Java. So my reference is like if you want to do hello Java in Python, how many of you don't know Python? Okay, everybody knows Python or no? Okay.
Stick to Java.
All right, anyway, if you want to do hello world in Python, you just say print hello world. That's it, right? It's a one-liner. And that's super easy because all you need to know is that there is a system function called print, or in JavaScript, you say console.log, and then you can log something to the console, right? You don't need to know all the machinery behind to do a hello world. But if you want to do hello world in Java, you have to know about imports, you have to know about classes, you have to know what final static void means. You need to know what the entry point is, you need to know what the parameter arrays are, you need to know what system is and what are streams. And then once you know all of that, you can put it all together into like 6-7 lines of code which prints hello world, okay? On Android, that grows even further, right? And if you're doing OpenGL and you need to open the context and create a window and do shit like this to do a hello world, hello triangle in OpenGL, it's like, I don't know, 25 lines of code, right? Or 30. If you want to do it in Vulkan, it's like 500 lines of code, okay? So it depends. On mobile, you need to know quite a bit to do hello world. That's why the first lab is kind of it sounds very simple, and once you know all those kind of building blocks, it's very simple, but you need to get to know that. So we will spend the second half discussing that a little bit. All right. Why I'm talking about Android philosophy so much will become clearer after tomorrow's lecture. So for today, you just have to take it for granted. Okay, so what is Android? Well, it's an open source mobile platform. You can, say it like that. It's Linux based, so underneath you have Linux operating system, Linux kernel. Why they decided to use Linux? Well, if you have a hardware platform and you need to have applications developed on it, you have to have some sort of a hardware abstraction layer. So you need to use something. So for example, Nokia was developing Symbian OS and proprietary operating system. You have a number of closed source operating systems for various mobile platforms. We will discuss it tomorrow a little bit more. You had Microsoft, which just killed the different the mobile phone, the Windows phone or Windows Mobile. How was it called? I think it was called Windows Mobile. So a couple of weeks ago, they decided, okay, there is no point. We're not doing it anymore. But you need something. So when Google was kind of coming up with their own platform, they had to either develop something from scratch or use something existing. And Linux kernel has, a well-defined history, well-defined drivers, and it was really good to use something that they can reuse, which had a security built-in and so on and so forth. So they decided, okay, we're gonna stick to that. They didn't do it on their own. There is a Open Handset Alliance, which at the time of writing that slide was 84 companies which were participating. They created the specs and they created the constraints of how the platform looks like. And it has a huge number of partners. So all the various manufacturers, hardware manufacturers, and also software manufacturers are kind of participating to develop for and on that platform. And initially, Google made it, the Alliance made it really open, but then they've noticed that some of the things are kind of hurting the ecosystem because of the partitioning. So with the last, I think, 3 releases, Google is kind of setting the minimal requirements of what is necessary on the platform to exist to be called Android. If you don't have those things, you cannot call it Android because it's some variation which violates the core principles, okay? And it's available on a number of devices. So you have it on the phones, you have it on tablets, netbooks, TVs, cars. It is a truly diverse ecosystem. So I've mentioned the Android open source project, and it is something you can read more on. And it kind of demonstrates that the Android itself, it's not just an OS. It's not just an operating system for phones. It's the entire platform. And I quite like the stack that they depict on the, which they depict on their website, which kind of puts everything fundamentally on top of the Linux kernel, which creates this kind of hardware abstraction layer, right? So you have this to isolate all the software-defined things from what the hardware constraints are, right? You always do that, like in any architecture, you try to abstract yourself from the underlying layer, so then you have this kind of a layer of independence. That block is not truly separate, although there is a well-defined HAL layer in Android, but it's kind of tightly integrated with the Linux kernel, okay? Then you have native libraries and Android runtime system. The runtime system is evolving. So initial runtime system that Android was using was Dalvik. Now they have the Android runtime system, ART, which is more advanced version of that. And that's how all the machinery is kind of plugged in together. It's very interesting if you're into the core computer science kind of architectural designs to look into how they're doing those 3 things, how they combine together and how they work together, right? So you have to have native libraries. Those are usually written in C, C++, or assembly. Then you have the runtime systems which glues the runtime libraries, native libraries into the runtime system. And then you kind of create this Android framework. And initially, that was strictly Java, right? Even though this is mostly C++, this was strictly Java. So to do anything on Android, you have to do all the programming in Java. The developers were kind of complaining a little bit because they were saying, well, we have a lot of C++ code bases, we have a lot of C++ games, and so on. It would be much better if we have direct access to this layer through the C++ interfaces. So Google, over the last few years, was making efforts to open up all the C++ APIs, and now you almost have the same. You can either access this purple and orange layer through C++ or Java. Going through C++ is much harder, though. It is much low level. You have to manage memory yourself, and it's much more complicated, but it is possible. So integrating native libraries with this layer is simpler now, okay? And then you have the applications developed by the developers. So what's interesting about that stack is that that stack hasn't really changed from the very beginning, right? When the Google engineers designed the platform, they sort of designed it this way, and it stays this way because it's a good design. You can improve this, and huge improvements have been done in the HAL layer. You can improve and add native libraries, and the Android runtime is evolving, and also you can kind of open up more, as I was saying, APIs, like outside of Java, you can have a C++ APIs and access this, and then the developers can build the applications. You can make the applications being web-based by providing special, web core technologies in those layers. So the whole thing works really well. To compare it with what Apple was doing, the architecture was really different. When Apple designed iOS, they thought developers will never code native applications. They will only do web applications. So the initial iPhone was designed as a web interface to web apps, okay? You couldn't do a native apps on original iPhone. And developers were trying JavaScript, and they trying HTML technologies back in a day, which were pretty crap back in a day. And they said, come on, it's like, doesn't work. We want to have native. So they jailbroke iPhone, and they tried to develop applications using Objective-C, using the native APIs, which the Apple architecture had, but never exposed to the developers, right? And then after a few iterations, Apple decided, okay, well, we have to have native support as well, because that's where most developers' value is, right? So they had to redesign the whole concept, and they were mistaken thinking that smartphones will only be used as a gateway to web, right? Smartphones are not only a gateway to web, and I hope this course will kind of show that. So even though the web technologies are evolving and becoming better and better, smartphones and mobile apps are not only a gateway to the web systems. They kind of have a life on their own. And there is a lot of native apps which are taking advantage of the native platforms which they run on. So in this course, we sort of focus on the native capabilities, both of iOS and Android. We will touch towards the end a little bit about the web-based frameworks, but I want you to kind of appreciate the complexities and the decisions which are kind of shaped by market forces. So when Google was kind of doing it, they had a kind of a good foresight. They predicted of what may happen. When Apple was doing it, they were mistaken, and they had to fix that, okay? All right, so because of that, because of the Android being a platform, you have a huge fragmentation. So as the previous slide was showing, you have over 300 hardware and software manufacturers. That number, actually, by the way, was written 3 years ago, so I haven't checked how many are currently, but it's probably doubled. So the number of companies supporting it and providing applications is enormous. So how do you deal with that fragmentation? Well, it is complicated. So we will spend some time kind of discussing it. All right, so let's go over the tower, the tower that I showed before. Very briefly discuss what they contain. So I already said that the decision was made to pick something that had a kind of a well-defined driver model, and well-defined security model, right? And the choice was, okay, let's use Android, let's use Linux kernel. The second thing was, when you're building a device with an operating system which will run multiple vendors' applications, right? So again, Android and Apple were different from the design point of view because the original iPhone was single-threaded. You couldn't run more than one thing at the time on the phone, right? So imagine that you're playing a game and then someone rings you, the game basically shuts down, you have to take the call, and then once the call is done, you have to restart the game because the game was killed. You cannot have two threads running at the same time on the original iPhone. Android, from the other hand, was from the very first day designed to be multi-threaded, right? So you can have multiple applications running together at the same time on the same device using the same CPU and same machine, the same RAM and same, drivers, okay? So what will happen? So let's say, what will happen if you on your PC run an app that is malicious to you? So what will happen if you logged into your PC, download an app which can wipe your hard drive and run it? What will happen? Come on. You just downloaded an app which will wipe your hard drive on your PC. You say run. What will happen? It will wipe your hard drive, right? Of course. Why? Why it will wipe your hard drive?
Because you have the rights to...
Because it has the same rights as you, right? You kind of logged in, and you're running the app as you, and it says wipe the hard drive, and it does it, right? Okay, so now I run an app which is good, and I run another app which is malicious, which is doing something to the other app. Can it do it? Sometimes it can, sometimes it doesn't, depends on how the memory protection works, but they both see the same hard drive, they both see the same things, and they both run as the same user, okay? So there is no real clear protection of me installing an app which is good and installing an app which is malicious, doing something malicious to all the good apps, okay? If the bad app wants to delete the database of the good app, it can, right? Okay, so now we have a problem, because I have a phone which I will install apps on, and those apps can be good or bad, right? But I have to clearly isolate them. I have to make sure that the bad apps will never harm the good apps, okay? So how is Linux doing that? Well, Linux is not doing that. So if, as we mentally discussed it, if I install a malicious app on my Linux, account, and I run it, it will do malicious things, right? But if I have malicious user and a good user, and the good user has his own files and its own databases and apps, my apps cannot hurt the other user because Linux has a very clear multi-user support where permission system for files and for memory protection and so on is so well defined that if I have two users and one is trying to delete files of another, it will not work because of the protections, right? So Android designers, they thought, okay, let's do that. Let's use it. Let's use the Linux multi-user model. And because we know on the phone you will have only one user, there will be no, multiple users. A phone is a device for a single user, right? But we have this technology which allows multi-user support. So instead of using this multi-user support for users, we will use this multi-user support for apps. So every app will have its own user and its own permission system, and no apps can kind of cross-contaminate each other because Linux is kind of well-defined across multiple users. So they kind of took advantage of the multi-user support of Linux kernel and Linux operating system to isolate all the apps into their own contexts, right? So if you now install a good app and a malicious app, the malicious app will have really hard time messing up with all the good content or stealing some good content from the good apps because they kind of using the Linux protection mechanisms to prevent that. Yeah, a caveat, of course, it's possible. You can have some exploits and you can kind of find some problems with that. But on the conceptual level, that was the decision that they've done, okay? Apple had to do the same. So for Apple or any other mobile operating system, you have to do the same. You have to isolate a particular context of the app so in such a way that other apps cannot read its files or mess up with the content. So we had kind of a very good multi-threaded process support. We had a very good multi-user support, which was used for the applications. We had a good security model, which was constantly evolving and constantly being reviewed by the community. So if you want something secure, Linux kernel is pretty good because it is patched and kind of helped by a number of open source developers. Networking is really good as well. It's actually superb. So if you dive really deep into the way Linux is doing networking, it's a marvel. Okay. So there were other operating systems which were pretty good. For example, Sun OS or later Solaris, the one from Sun Microsystems. That was really well designed and engineered operating system with really good network support as well. But it was, I mean, from the engineering point of view, it's so much easier to read it and to kind of understand how it works. But performance-wise, Linux is like much, much, much better. It's much harder to understand how it works. It's kind of a very messy collection of code, but it's very highly optimized and really good. All right, so it was kind of a natural choice. So they started with the kernel 2.6. I've been doing those slides for 4 years. So every year I'm updated. So I've checked yesterday, and my phone is running the latest kernel, which is the 3.18. And what we have here, we have all the kind of a driver support. Yeah. Yeah. So what we have here, we have the display driver, so we can plug in various drivers for the GPU that you're running on the phone. We have the camera drivers, again, for different manufacturers, for different cameras. We have the flash memory. We have the power management, audio drivers, Wi-Fi, keypad if you have a keypad, and so on. Like nowadays, you don't really have smartphones with the keyboard, but if you see on this picture,
Dead now?
it's dead.
You killed my...
I didn't touch it.
Those Mac users.
Okay. Yeah, so as you see, this one here, that's the Android phone with the keyboard. You probably haven't seen one like that for a couple of years. But yeah, anyway, some had. Do you want to say something?
Is it a different kernel from what you run on your PC?
Yes and no. Yes and no. So it is a different kernel because it has to deal with slightly different things, and it has to have a very small memory footprint. So they cut off a lot of things. Like it doesn't have to deal with a number of file systems and so on. Like it's not expected suddenly that you plug in a particular file system, so it has some limitations, but it also is the same. There is no real difference between that kernel and the real Linux kernel, right? So it's basically the same code base stripped down to what they need. So a side note, there is a little bit of controversy as well, because initially Google was using Linux kernel, but for a couple of years they didn't submit any patches to the community, and the community was saying, look, Google is using our technology but never contributes back. They kind of don't reciprocate the goodness that they are using, right? So then Google got a little bit bad publicity for not submitting like security patches or things like that, and they really changed around. So from being kind of a non-Linux kernel contributor, they became one of the most contributing contributor. So they make sure that all the internal technologies that they kind of developing and so on are being given back to the community. So they are kind of doing the voluntary support of the kernel as well. All right, so then we have the native libraries. So what we have here is we have to have a lot of support, which is not directly hardware related, but is generic enough that it needs to work across multiple things, right? So for example, we have, libc support, right? So the core system level libraries for doing printouts. We have SSL support, we have OpenGL support, we have the Surface Manager, so kind of like the things on top of OpenGL for graphics. We have the media framework, we have the fonts, and we have a database, and we have a WebKit. So WebKit is an open source rendering technology for HTML, and both Android and iOS are using it. Chrome is using it, Safari is using it. So it's kind of a fundamental technology for the web technologies. Yeah, the one more word about database support. So normally if you have a platform, you have to have some sort of a database support for persistent storage. We will discuss it later in the course. And the early decision was to use SQLite, which is sort of like a very minimalistic SQL-like database for storing structured data. Recently, a lot of people were complaining that, first of all, it has its limitations in terms of how you're storing the data, and also in terms of performance. So there are alternatives. So last year when we were running the course, instead of using SQLite database for persistent storage, some students were using kind of an abstraction layer, which gives them ability to plug in different database systems underneath. And then you are kind of more flexible of what you want to pick. So it is possible to use something else than SQLite these days. All right, then we kind of getting into the Android runtime. I can spend entire lecture or two, or maybe even a course, discussing just that bit. Again, it's kind of a marvel of engineering, of how you can manage to optimize what Java is effectively doing with a virtual machine into something that is super cool. Okay, so Java virtual machine is stack-based virtual machine. So it works in the context that you have a kind of a central processing unit, and then instead of registers, like with the normal architectures like Intel, you have a stack. So you put your parameters of the calls onto the stack, and when you call them, you pop them from the stack, right? So instead of saying add register A with register B, you say add, and then two values are popped from the stack, added, and the result goes onto the stack, right? So why? Well, because conceptually, stack-based virtual machines are so much easier to describe, and then the implementation details are left out. Like you can implement them the way you want, but you kind of in a very concise way, you can have a very small instruction set and have kind of a very verbose and robust virtual machine, like instruction architecture. But you cannot have that on the mobile platform. Mobile platform uses mostly ARM CPUs. They are register-based, and having this translation layer between this abstraction and the actual runtime has to be done somewhere. And if you're doing it on the system, on the runtime system itself, then you will be really slow. So you kind of see that with some of the Java on a PC, the kind of a loading time and bootstrapping time is usually quite slow compared to anything else. Once it warms up, once it's kind of compiled, just-in-time compiled to native code, then it works really well. But this initial step is a little bit cumbersome. So what Dalvik was doing, they were kind of taking they redesigned the virtual machine completely, and they've used a register-based virtual machine instead, right? And that leads to this kind of side topic again between the lawsuit of Oracle and Google, right? So Java was a technology developed by Sun Microsystems, and they proposed the specs, they proposed the language layer, like how the Java syntax looks like, and then they proposed this virtual machine of how it works, what is the instruction set and what not, right? And then Oracle bought Sun, so Oracle became the IP owner of all of that. And then Google kind of developed Android on top of Java, but they never used the VM. They only used the Java syntax, right? So if you compare what is Java doing on a PC and what is Java doing on Android, apart from the syntax, everything else is completely different. There is nothing the same, right? So it's like saying, if you say main, so if you come up with a language, and if you say void main, and you're using that, and then C++ says, yeah, that's C++, that's us. You say, no, it's just a language which looks like C++, but I call it D, or I call it whatever, right? It's not your technology, we're just using that. The API looks the same, but what we're doing is completely different. We're doing it our way, right? So Google was saying, look, the APIs look the same. The calls look the same. But what we're doing is us. We develop all the technology ourselves. We're not reusing your technology, right? So Oracle sued Google about that, whether the APIs are owned by Oracle or not. And they kind of lost their lawsuit because you can't really lock and copyright the APIs, because if you do, then the whole computer science and developers world collapses, right? Because if someone copyrighted printf, right? It's like, come on, you can't copyright printf. It's just an API. It's just a way of interfacing between systems, right? The way you implement the systems, you can copyright and protect, because you may have a very smart way of doing something, but the way it is called, you cannot copyright that. You cannot block people calling things the same way as you called things, right? So that's kind of interesting, because people say Android is using Java, which is kind of correct on the syntax level, but there is nothing Java inside the VM itself, right? They completely redesigned it. So why? Well, because you first of all, you have a limited memory footprint. You have memory speed as well, limited speed. So the early Android devices were quite small, quite constrained, and quite slow. So for them to become kind of usable, you have to do something, right? So the very the generations which happened were that Java source code is compiled into the .class files, which are then interpreted by the Java virtual machine and compiled by just-in-time compiler to the native code of the platform, right? That's how Java kind of works. With Android, you compile the Java source code into the class file, then compile the class file into a DEX file, and then you use the DEX file to re-index all the symbols and everything and have kind of an intermediate format. And then you compile it to a native code after you've done all those initial steps by the just-in-time compiler. So they introduced just-in-time compiler in version 2.2. Before that, all the code was kind of interpreted based on the virtual instruction set which they had for the VM, right? Again, a side note, Google didn't develop Android from scratch, neither, right? So when they were deciding to do the platform, they said, okay, we need something for the hardware abstraction layer, let's Linux. We need something for this, we need some VM technology, right? So I can't really use the laptop, but if you Google Dalvik and Iceland, you will find out that Dalvik is a very small village in Iceland, where one of the developers was living and working on a cool VM project for himself, right? So he was developing a virtual machine which had kind of instruction set which the Java VM has on Android, and Google bought them, right? So Google bought his technology, and he became the core architect of Google virtual machine for Android. And it is quite cool because, it is just one person project in a sense, which kind of started the whole Android thing, right? So if you combine Linux kernel with his VM, basically you have Android. That's what the pre 1.0 version was. It was one-man project with a Linux kernel, right? So you can think of this Android runtime as being kind of massive, complicated thing with thousands of engineers working on it. But in reality, any of you could start something like that, right? You could use Linux kernel and put an extra layer on top to have something like Android developed. So it's not impossible. It happened. So the evolution was before 2.2 there was no just-in-time compiler. So do you know what just-in-time compiler is? Okay. You didn't have operating systems?
We're having it now.
Okay. So normally if you have a physical layer, physical CPU and physical layer which has to execute like an Intel instruction set, x86. Then you have some sort of kernel, an abstraction layer, but the kernel and the abstraction layer also uses the kind of the instruction set of the underlying hardware. And then you may have a virtual machine which has its own instruction set, right? So in the context of Java, like the normal Java, you have the Java VM with the Java bytecode instruction set. In the context of Android Java, you have the Dalvik with the day instruction set. This instruction set defines a program which cannot be interpreted by ARM or Intel CPU. It's kind of an abstract instruction set. And it has to be translated into the native instruction set of the hardware, right? How you can do it? You can run a compiler to generate the binary which is in the instruction set of the hardware, or you can load it into the memory, and as the calls are made, let's say I'm calling a function A, and then I have this instructions for call A, I then compile them for the native machine code, right? So if you pre-compiling everything to the native layer, you're doing like a compilation step. And if you're waiting until it is called, then you're doing just-in-time compilation, right? Because you don't pre-compile everything, you only compile the bits which you need to run. And the bits which you're not running, you don't compile. So what's the advantage? Well, the advantage is that if you have a kind of a complicated game, for example, it will take a long time before everything is compiled and you can run it, right? But once everything is compiled and you're running it, there is no delays, okay? When you're doing just-in-time compilation, it loads immediately and it starts immediately because you're just doing some simple thing which is fast to pre-compile. But then as you use more and more code, you have to kind of compile more and more things. So if you only have one core, and you're balancing those two things, usually pre-compilation works better, right? Usually just waiting a little bit longer when things load, pre-compile and run is a better strategy. And that's what happened with the early versions of Android, because we had headsets with a single CPU, right? But if you have a multi-core box, some of your mobile phones now have 8 cores, right? You can use 4 of them or 7 of them to run the game, and 1 of them to keep pre-compiling new things that will gonna run later, right? And you will not see much of a performance penalty, and things will kind of load much faster and seemingly work faster, right? So from version 2.2, Google decided, and the technology matured enough, that we could take advantage of the multi-core support. So that's what happened with 2.2. There were huge performance improvements from version 2.3.4, right? If you have to support devices before 2.3.4, you probably working in a very niche environment, right? We typically don't support anything below 2.3.4. All the support libraries are from 2.3.4, so it's kind of like the bottom of the pyramid. And then in version 4.4, Google decided that the original Dalvik technology is old enough that we need to replace it with a new, and there was a switch. So they switched from the Dalvik VM to ART, which stands for Android Runtime. So it's kind of you can think of it as Dalvik being part of ART now, and ART is sort of just-in-time compiler and ahead-of-time compiler, right? So because we have multi-core machines, we don't have to pre-compile everything up front, but we don't also need to wait until things are called. We can predictively say, okay, we expect in near future the call to go to this to this call, so we can pre-compile it ahead of time. So we have 2 technologies now, which is called just-in-time and ahead of time, and they kind of work together. All right. So let's have a very short break, like 4 minutes, and we meet 6 minutes. We meet here quarter to 10. Okay.
Where was it we could watch the slides online?